Thank you very much to the presenters and the audience for being here today. This is our third doctoral meeting session. It's a quite exciting session on again, electric propulsion for space environment. And we'll be having today 7 presentations by Maria Sherezade, Celia Boyé, David García La Huerta, David Madaloni, Víctor Gómez García, David García Villegas, and Borja de Saavedra. Basically, we're going to be today listening to 3 presentations on the Zarathustra Starting Ground project that Mario presented to us in March, and you have the presentation and the recording should you want to check what he's proposing. So it will be a good opportunity to listen to his project. Maria will be presenting her thesis on Micropulse plasma thruster design. So again, an experimental PhD thesis, very interesting one. And then we'll be hearing to 3 industrial PhDs with CENER and ENI Space. ENI Space indeed is a spin-off of some research that was done in EP2 group 2-3 years ago. So it's very interesting also to see what we are being able to transfer to society in the form of a spin-off and new positions for people and groundbreaking research. As you know, the presentation should be 10 to maximum 15 minutes long, right? So keep an eye on the time. We will be strict on the time, right? Because then we'll need some minutes for questions.
So hello everybody, thanks for being here to listen all these presentations. I'm going to present my thesis about the prototype development and testing of a magnetic arc thruster. So my thesis directors are Mario Merino and Jaume Navarro, which are in the audience. And I began this thesis a few months ago at the beginning of the year 2021. So very quickly, the contents of the presentation will be the Zarathustra, because that's the name of the project. I will explain it to you later, motivation and goals. Then I will go to the first characterization to finish with the magnetic field simulations and also the power injection definition, as you will understand later in the presentation. So to begin with, this thesis is about electric propulsion, obviously. Traditional plasma thruster performances and lifetime, they are limited by the presence of electrodes. And these electrodes, they are constantly bombarded by high energy particles. This is really bad because it's limiting their lifetime a lot, and also they have an inability to adapt power, scaling, and flexibility. These 2 disadvantages are added to a third one, which is the small throttling range in terms of thrust, specific impulse, and power. So this is actually, these big main disadvantages are limiting the lifetime, the efficiency, and so the use of these thrusters. Also, they have to be used with an external electrode, which is the hollow cathode, and it requires a constant flux of gas to generate a plasma bridge. This neutralizer, which is actually the hollow cathode, it remains a critical component of the traditional plasma thrusters, and they use xenon to avoid contamination of the electron-emitting insert, which is the main component of the cathode, in the use of other propellants such as iode, diiode, or any other propellant you can think about. So here we come with the electrodless plasma thrusters. These thrusters include a variety of concepts. There is a lot of them, like the ECR, the one I will present in the next slide. There is the HPT, which is the one developed in the lab, and also the Vasimir, which is another thruster developed by another university. These concepts, they use the plasma generation and acceleration without any electrodes in the plasma. So to do that, they use, as you can see in the image, next to the text, they use an antenna, which is this antenna here, or another type of antenna, waveguide if you want, or some coaxial cable, and some magnetic field to produce and carry plasma. The actual magnetic field applied inside the source has 3 functions. It enables the propagation and the absorption of the electromagnetic wave mode. It reduces the plasma losses to the lateral walls of the vessel, and also is generating a diverging magnetic topology outside of the thruster, which can be named as a magnetic nozzle. And to finish with, an electromagnetic field radiator delivers the electromagnetic power to ionize and heat the propellant into a plasma. This is the antenna you can see in this image, but as I told before, it can be many other power injection methods. In the Doctoral project, we are focusing more upon which is called the electron cyclotron resonance principle to generate the plasma. So in the magnetic field, electrons they have a circular motion due to the Lorentz force. But when this motion is overlaid by an axial motion, it transforms into a cycloid motion. And this cyclotron motion is in fact defined by the strength of the applied magnetic field. So as you can see in this scheme, when you have a coil a coil generating a magnetic field, and also a power injection, which is, as I said, can be microwave guide, antenna, and coaxial cable, the electrons will be excited, if I can say so, and then will collide the ions, which will then face the magnetic nozzle coils, which are not present in this scheme, but which are mainly here into the EPTs usually. The ions are then expelled and accelerated out of the thruster. And so, as I say, so the plasma generation is enabled by the collision between electrons and neutrals. EPTs may present many disadvantages, especially regarding incomplete understanding of plasma heating and transport, and inherent limitation in cylindrical thruster designs. If you remember, one of my colleagues, Marco Ingingolo, made a presentation about cylindrical thruster, an EPT1 last week. So the magnetic field lines, they intersect the rear part of the ionization chamber. And so that leads to the loss of 50% of the ions created. Also, the magnetic nozzle consists of a diverging magnetic field lines imprinting a high divergence angle to the plume. These disadvantages, it reduces the thrust efficiency to not much than 20%, but as usually, traditional plasma thruster, they relies upon something like 30 to 40% a range of efficiency, and so this is why they are commercially competitive. This is why we are producing this new project, Zarathustra, which means revolutionizing advanced electron-less plasma thrusters for space transportation. This thruster, it relies upon the principle of replacing the cylindrical geometry, as you have seen before in the scheme, by a U-shaped configuration to solve EPT's classic issues. So the generated magnetic field is everywhere parallel to the thruster wall, so we don't have any more issues about collisions between ions and the wall, especially at the rear part of the thruster. And also the magnetic nozzle issue is solved by a closed line magnetic field geometry. Compared to classic EPTs, the Zarathustra thruster could bring the advantages of reducing, obviously, the plasma losses to the wall up to 50% because we don't have any more rear parts in the thruster. And also by lowering the plume divergence, the magnetic interference, as well as the magnetic, sorry, I missed myself in my head. It's also lowering the plume divergence, the magnetic interference, and as well as the magnetic typo, sorry, by using a closed line magnetic topology. Anyway, moreover, it allows first vector contactlessly by controlling the magnetic field strength. This is something we'll have to look for further into the project, but by controlling independently all the coils, we'll be able to modify the thrust of the thruster and to make some thrust vectorization. So what is the main functioning scheme of this thruster? First, a neutral gas is ejected in the center part of the thruster and ionized by the applied electromagnetic field. Then the applied magnetic field guides the plasma to the exhaust and the chamber and shields the walls to enable the absorption of electromagnetic wave. And finally, the plasma expansion begins at the glass coil of the thruster, which is kind of magnetic nozzles, but with opposite polarities. And to finish with, the plasma-induced magnetic field deforms the magnetic arch, and it enables the excitation of the plasma to create thrust, like a classic thruster. Now we are at the very beginning of this project. The first step was to make the characterization, especially the geometric characterization of the thruster. So I took the decision to make this thruster of 5 parts. As you can see, 3 straight parts linked by 2 curved parts. And to help the magnetic confinement, I used 3 different coils, which you can see here in blue, red, and green, which are, as I said before, this magnetic nozzle, which can, like these 2 coils, which are acting are like magnetic nozzles, but with opposite polarities. These 2 curved coils, which are guiding the plasma inside the thruster, and also these 2 principal coils, which are helping to have a very good magnetic topology in the center part of the thruster. And so in order to iterate as fast as possible, all the dimensions of the thruster are a function of the characteristic length L, as you can see here, which is the minor radius of the torus. This helps us a lot because we are able to iterate very, very fast regarding this length and to change all the parameters to play with regarding the magnetic work or also the power injection work. For now, the CAD is made on CATIA and also Autodesk Inventor. And as you can see on this side, this is like the first CAD product, let's say, of the thruster, which is we'll have to improve this a lot more to be able to have the first prototype. Also, we have parameterization going with Excel and CATIA, which is making able to iterate as also very fast and to also iterate between MATLAB, CATIA, and Excel without changing all the parameters. One of the main aspects of this project is the sizing of the coils, because the coils will be responsible of guiding the plasma and also protecting the walls, and so making the thruster efficient. So I'm using the magnetic field repository made by Mario Merino to simulate the magnetic topology of the thruster. So first of all, I'm making a 3D model of the thruster with all the coils plotted as loops, because it's making the computation way more easy than like classic coils, let's say. I'm also putting the 3D magnetic lines, which are generated to improve state-by-state magnetic topology. And finally, I'm using a 2D color map of the magnetic strength with the 875 Gauss line to increase the resonance surface along the chamber, because this line of 875 Gauss is the one which is responsible actually, is the surface, the line, because we're in 2D, but the surface on which the ionization will be made thanks to the electron synchrotron resonance. I remind you the formula, let's say, of this resonance, which is here, and this is why we are achieved to get 875 Gauss, which corresponds to actually the 2.45 gigahertz frequency. Also, we are dealing with some power injection issues, not issues, but I mean work pen issues. The power injection is still a work in progress, and I'm running simulations into ANSYS HFSS to determine the best power injection configuration. So for now, we have kind of two configurations which are very stable. Which is, the first one is the coaxial cable, as you can see here, with kind of a cone, and it's injecting the power thanks to a dielectric window. And also we have another type of power injection, which is to put the coaxial cable directly into the chamber to emit some electromagnetic waves. The next step of this project, at least for this beginning thesis, is to 3D print and assemble the thruster to test the design and to see if everything is good for to make the real model and to other parts. I want also to finish the electromagnetic simulations and to improve the magnetic topology as much as possible, as well as the power injection. Also, we might have some thermal issues. So especially regarding the coils, because of the power in the coils. So I want to run thermal simulations. And then in the next month, we will order the first parts of the prototype to complete the first assembly, assemble them, and testing them to see in vacuum to see if the proof of concept is real and if we can have a good thruster out of this bright idea of making this U shape instead of this cylindrical shape. So here are my references, and thank you a lot for listening to me.